Let's take a look at the key concepts out of this module's material. So first, if you separate species that react by the transfer of electrons from one to another, that allows you to use that potential difference in order to transform it into work in an electrochemical cell. And by adopting a convention for the standard potential of 1/2 cell, and we choose, the whole world's community chooses, the standard hydrogen electrode as the cell to be chosen, then measuring full cell potentials lets you relate all other half cells back to the conventional half cell, which in the case of standard hydrogen electrode is defined to have a cell potential of 0. Debye-Huckel theory proved useful to us again because it permitted us to determine standard cell potentials by being able to extrapolate experimental cells back to 0 concentrations of electrolytes. The Nernst equation is the key equation in electrochemistry. It relates an actual cell potential to a standard potential, which refers to all participants in the cell being at unit activity, minus RT, gas constant times temperature, divided by number of electrons being transferred within the reaction, and the Faraday constant, and the log of the reaction quotient, which includes the actual activities or concentrations. And through manipulation of the Nernst equation, we're actually able to assign thermochemical quantities, free energies of formation, enthalpies of formation, entropies of formation, to ionic species in solution. And that gives us the full range of thermochemistry in aqueous solution, in any solution actually. So electrochemical cells are moreover useful for measuring things that would otherwise potentially be quite difficult to get at, certain kinds of equilibrium constants. We saw the example of a silver chloride solubility product, for instance. They're also quite often used to measure acidity constants for weak acids. Batteries and fuel cells are the ultimate practical realizations of electrochemistry, and I spent quite a bit of time looking at a few of those. And the last point that was made in the most recent lecture is that solar photons can in principle be harnessed to catalytically split water and generate hydrogen as a clean solar fuel, where we can exploit that hydrogen very effectively in a fuel cell to capture the energy of burning it. The fuel cell burns it by combination with oxygen, but in a very controlled way. All right. That is the end of statistical mechanical thermodynamics. The train, the first law train, has actually reached its destination. So I and the Wolf want to thank you for riding with us. We certainly offer you all the best wishes for future journeys on other trains of your intellectual interest. If you have come to this point and you found it to be useful and you want to drop some feedback, you are more than welcome to do so as well. But in any case, best wishes, do good work.